Welcome. Today is December 4th, 2020, and this is a NERI webinar intended to disseminate educational information and research outcomes around natural hazards and the built environment. In today's webinar, we explore an emerging area of nature and nature-based features affecting the attenuation of waves and water levels in coastal flooding hazards with Professor Tori Tomaszek. This webinar is hosted by the Natural Hazards Engineering Research Infrastructures, Computational Modeling and Simulation Center, and the NERI facility at Oregon State University's O.H. Hinsdale's Wave Research Laboratory. This webinar is supported by the National Science Foundation under awards 1612843, 159679, and 1520817. Any statements in this webinar are those of the presenter and do not necessarily represent the views of the National Science Foundation. For more information about NERI, the Wave Research Laboratory, and the SimCenter, visit designsafe-ci.org, where you can find links to the SimCenter and the facilities supported by the National Science Foundation. Today's webinar includes two parts. First, we'll have a presentation by Professor Tomaszek, and then we'll have a live experimental test run at the wave flume at Oregon State. And in the conclusion, we'll have some question and answers by the attendees. Professor Tomaszek is an assistant professor at the U.S. Naval Academy. She has a PhD from the University of Notre Dame and completed a postdoctoral fellowship at Oregon State University. She has participated in field reconnaissance surveys evaluating damage and recovery of near-coast residential structures, and she has experience with physical model experiments at the U.S. Naval Academy, Oregon State University, and Kyoto University. Her research interests are to better understand wave-induced forces on coastal structures and the performance of natural and nature-based infrastructure to inform the successful implementation of sustainable, resilient coastal engineering solutions. The title of her presentation is Reduced and Prototype Scale Physical Modeling of Wave Attenuation and Wave Force Reduction by a Mangrove Forest of Moderate Cross-Shore Width. Professor Tomaszek, thank you for joining us, and I invite you to begin.
Thank you so much, Matt. And I'd like to thank you for the opportunity to share some of our work today. I'd also like to thank everybody for joining and also for your patience as we work through some technical difficulties. I'm really delighted to share some of the results from this project, which has actually been ongoing for a couple of years. Here is sorry, just one moment. Here you can see an outline of what I'll be talking about today. Here you can see an outline, sorry about that. This project actually was motivated by a reconnaissance study we did after Hurricane Irma in the Florida Keys in 2017. And based on that study, we found a real need to understand the engineering performance of mangroves in terms of wave attenuation and force reduction. And so based on our observations in the Keys, we built a reduced scale physical model at a 1:16 geometric scale. I'll share some results from that study before talking about the prototype scale physical model that we have constructed and are currently testing in the Oregon State University large wave flume. Then I'll jump over to a live demonstration where we'll actually show you we're running waves today before sort of wrapping up, and I'm happy to take any questions. So as Matt mentioned in the introduction, natural and nature-based features are an emerging area of research for coastal resilience and coastal hazard mitigation. It's very important to understand how these systems perform, not just from an ecological perspective, but also from an engineering perspective in terms of wave energy dissipation, load reduction, and flood storage capacity. Here you can see some of the examples of natural and nature-based features implemented in urban environments. These are concept designs right now, but I think these designs are moving forward, such as the Big U in New York City, the Emerald Tutu in Boston Harbor, as a design idea. And also this Fort Pierce Marina, it's actually a constructed island living breakwater that's being used to protect the marina. This was identified in the Nahiri 5-year science plan as an important area of future research. The background and motivation for this study again occurred after Hurricane Irma in 2017. Here you can see some of the hydrodynamic conditions that occurred during Hurricane Irma. The track of Hurricane Irma is indicated by the black line you can see in each of the panels. And we've plotted the Coastal Emergency Risks Assessment hindcast of the inundation depth, significant wave height, and wind speed produced by the storm. Our study area was Key West and Big Pine Key, which are indicated by these black boxes in each of the panels. And Key West, located to the left side or east of the storm, experienced less severe hydrodynamic conditions than Big Pine Key, which is typically expected based on the storm's rotation. We, after the storm, performed damage assessments, evaluating damage on a 5-point scale to the roof, walls, landscaping, and attached structures, foundation, and also the shoreline. Our goal here was to understand relationships between shoreline damage, structural damage, and hazards, as well as to understand how shoreline management could affect damage and recovery. We were able to survey 263 residential structures just 1 month after the storm made landfall. We actually arrived in the Florida Keys the day that they reopened to tourism, and so we were there before many of the reconstruction activities had started to take place. We also performed assessments of individual shorelines. One thing that's very unique about the Florida Keys, you can observe in the figure or the picture on the upper right-hand corner of this slide. This shows a overhead view of one of the neighborhoods in Key West. This is actually a Naval Air Station housing facility where you can see, as is common with many naval stations, all of the building footprints look nearly identical. But what's very different about each of these building parcels, particularly the waterfront parcels, is that as you move from the northern to the southeastern edge of this shoreline, you see a wide variety of shoreline archetypes. So this top one here has a sandy beach. We have mangroves as you move further south, and then finally stretches of revetments with sparse mangroves in between. And this was very common, this parcel-scale shoreline variability. I've shown you some pictures of the damages that we observed for various shoreline archetypes. Overall, one thing that really struck us during this field trip was how well mangroves performed during the storm. Only 1 month after the storm, we already saw signs of regrowth, and many of them looked unaffected by the hydrodynamic and wind conditions associated with Hurricane Irma, particularly in Key West, where the wind was not quite as extreme. Sandy beaches tended to be completely washed away, completely eroded after the storm. This may be in part due to the fact that Key West is built on lime rock, and so there's not a lot of native sand to the area, and so most of the sand was just washed right offshore. We also observed damage to revetments and bulkheads in the form of partial collapse of bulkheads, stone displacement in revetments. And our initial assessments, we attempted to relate the hazard intensity measures that we were able to obtain from the storm hindcast to the damage condition observed by the storm. And so the hazard intensity measure that we defined was the freeboard, which we defined as the elevation of the wave crest above the lowest horizontal structural member. So this elevation of the wave crest eta minus the elevation of the lowest horizontal structural member above ground. As that gets bigger, more and more of your house is inundated by the wave. So what we expected to see was, as this parameter increased, more and more structures experienced high damage. If you just look at this figure right away, it looks a bit like a cloud, which was somewhat discouraging at our first pass. It wasn't until we separated each of our structures by its shoreline archetype that we realized that most of the structures that experienced these severe hydrodynamic conditions but low damage states were structures that had mangrove shorelines, indicating that mangroves had provided some sort of protection during the storm. And this is actually not so new. There's a lot of other excellent studies out there that noted similar protection by mangroves during hurricane as well as tsunami events in Florida and Asia. But these studies often noted this protection occurring over kilometers of mangrove forests rather than the football field size mangrove forests or even smaller cross-shore widths that we observed in the Florida Keys. And so here you can see again some other previous studies of wave attenuation through vegetation, with many of them focusing on long mangrove or vegetation widths compared to the wave lengths. We were observing this protection occurring at fractions of the wavelength. And so this is what we set about to do with our reduced scale physical model. Before we could build our reduced scale physical model, we actually went back into the field to learn a little bit more about mangrove geometric and mechanical properties. So we went out to the field and we measured mangrove proproot diameters, trunk diameters, proproot density, as well as elasticity. We also consulted some excellent literature sources that talk about how to parameterize a mangrove tree based on the diameter at breast height. And we constructed a 1:16 scale of the mangrove forests that we observed in Key West, which you can see here. One thing you'll notice right off the bat is we removed the canopy. In part, this was because we didn't want to worry about the scaling effects, and also because most of the hydrodynamic properties owing to the storm surge and waves were interacting with the trunk and prop roots. These experiments were actually part of larger tests at Oregon State University. These were done in collaboration with Oregon State University, the University of Notre Dame, University of Southern California, University of Hawaii, and Hanyang University. And they investigated things including macro roughness, effects on hydrodynamic transformation, effects of seawalls, debris, and then we included the vegetation component. One thing that was really exciting about this test setup is that we were able to use 2 pumps, which we installed behind these wave dissipating revetment structures, and they allowed for the creation of a continuous flow so that we could superimpose waves over trailing currents. We considered 3 experimental configurations placed directly in front of the macro roughness elements on the horizontal test section. The first one, our baseline configuration, considered 0 mangroves. Our second configuration considered 4 rows of mangroves, which corresponds to about an 8-meter prototype scale width. And our third configuration considered 8 rows of mangroves or 19 meters of cross-shore width of our of mangrove protection. Here you can see another close-up view of our mangrove specimens, as well as some of the instrumentation we used during the tests. We considered a lot of instrumentation used solely to characterize hydrodynamics, including acoustic Doppler velocimeters, wire resistance wave gauges, and ultrasonic wave gauges, which were positioned both along the slope to characterize wave transformation, as well as in front of and behind the mangroves to determine effects of the mangroves on wave transformation. Each of these silver structures was also instrumented with either a load cell or array of pressure gauges. The one that was shielded the most by the mangroves was the 6 degree of freedom load cell, which is the that I'll be showing in a couple of slides. Here you can see a video of the tests, as well as the 3 different wave configurations that we considered. I'm going to let the video play again, but when I do, have a look at how the splash up changes as you look at the shielded silver boxes compared to the unshielded red boxes. All right, it might be having an issue with the playback, but I can tell you that the unshielded boxes actually had a very noticeably larger splash up than the shielded boxes, which was observed for all of our wave trials. We considered irregular as well as long tsunami-like waves. Today I'm going to focus on the on the tsunami-like wave conditions, which we increased the wave period while reducing the wave amplitude. Here you can see a time series of the water surface transformation behind our mangroves. This is located at a gauge in a side street directly behind our mangrove configurations, as well as the cross-shore velocity transformation as you move from a no mangrove case to 4 rows of mangroves to 8 rows of mangroves. The black lines in each of these time series indicates the 0 mangrove case, while the blue dashed line and orange dashed dot line represents our 4 rows of mangroves and 8 rows of mangroves, respectively. One thing that we can notice that's right away from these figures is considering the water surface elevation, we actually see an increase in water level behind the mangroves when we added mangroves compared to the 0 mangrove case. We also observed that there wasn't a large difference between the M4 and M8 configuration, indicating that adding mangroves had more of an effect than adding more mangroves. So the presence of mangroves was more important than the 2 different cross-shore widths that we considered. Similarly, we observed for the water velocity that the water velocities tended to decrease more quickly when you added mangroves. But again, there wasn't a very large difference between the M4, 4 rows of mangroves or 8 rows of mangroves. We also considered mangrove effects on inland loads using the 6 degree of load cell that I showed a couple of slides ago. That's shown here in this gold box. And again, we can see that as you move from the M0 or black lines for all of the wave conditions tested to the 4 rows of mangroves to 8 rows of mangroves, we see a clear reduction as you add more mangroves. This is good to show qualitatively, but we also were able to quantify that reduction by comparing the actual force measured against the increasing wave period, as you can see in this left-hand panel. And so this left panel on the x-axis, we have our representative wave timescale, and on the y-axis, we have the cross-shore force measured by the 6 degree of freedom load cell. Black circles indicate our no mangrove baseline configuration. Blue triangles indicate our 4 rows of mangroves, and orange squares represent 8 rows of mangroves. The shaded symbols indicate trials that we ran in the presence of a background current, while the hollow symbols indicate trials that we ran just waves over still water. And you can see that for all of our cases, as we added mangroves and added rows of mangroves, we saw a reduction in overall force. So these vertical lines indicate the same trial adding mangroves. We also see that as the wave period increased, the total force on the structure decreased in general. This was in part due to the fact that we also reduced the amplitude as we increased the wave representative timescale. This right-hand panel shows our cross-shore distance of shielding mangroves on the x-axis and our force on the y-axis. So you can follow a similar wave condition by following the same symbol. So our ERF3 was our shortest wave with the largest amplitude. We see it has a very large force when there's no mangroves, which is reduced quite a bit when we added 4 rows of mangroves, and even more when we added 8 rows of mangroves. But one thing that we noticed about all of our trials was that this load reduction was not linear. And in fact, we found a semi-linear relationship between the cross-shore thickness of the mangroves, or our vegetation width, normalized by our wave representative timescale times the offshore celerity of the wave. And so one thing that this figure indicates is that the longer your wave period, the larger expanse of mangroves you need in order to effect a given load reduction. But one thing we can also take away from these results is that the reduction that we're seeing here is significant even at very low percentages of the offshore wave representative period normalized by the celerity. So we see that even at these very small fractions of these values, we see a significant reduction. While this is promising, there's still a lot of questions that remain. And one of the biggest questions is, how does what we saw in the lab with these reduced scale tests actually scale up into real world mangrove systems? And so one thing that I think is really important to understand in natural and nature-based features is how the work that we're doing in the lab scales up to represent real world systems. One note that you always have with lab experiments is that it's very, very challenging to match your Reynolds number unless you do this at full scale. And so while our Reynolds numbers for our 1/16 scale tests were high enough to ensure turbulent flow and inertial forces dominated viscous forces, we're still orders of magnitude less than that you would expect in a real world system. And so I'm really excited about projects that we have ongoing right now with the Army Corps of Engineers and the project that I'll show you at Oregon State University, where we're actually constructing large scale versions of these mangrove specimens to see how wave transformation scales as you move from 1/16 to 1/2 scale to 1/1 scale, which is the test that we're running at Oregon State University. So here's what you can see, a image of the prototype scale experiments, an overhead view of our mangroves. The goals of these experiments are to quantify mangrove performance at full scale, both from a hydraulic response perspective, so wave transformation, as well as load reduction and attenuation perspective. We also are considering 2 different stem densities. That's something we weren't able to do with our 1/16 scale tests owing to time constraints. But in these tests, what you see here is our dense configuration of mangroves. Just this week, we actually harvested half of them. So we have a half density case that we're also going to compare how mangrove stem density and overall blockage area affects wave transformation and load reduction. And then finally, as I mentioned, we're really excited to assess how these systems, all constructed similarly, scale from reduced 1/16 to large 1/2 scale to full scale that we're doing in the large wave flume. Here you can see a view of the experimental layout. We're in the large wave flume, so upon wave generation, waves propagate over a flat section before they go up a 1/12 slope to induce wave shoaling and some wave breaking, depending on our water depths. We then have about 18 meters of mangroves before the waves either just propagate through to the beach or interact with a test wall, which is where we're going to be measuring the loads on the structure. And I'll show you a drawing of that in a second. We have 3 experimental configurations. And then each of those configurations is with and without a test wall. So we finished all of our trials with the dense configuration of mangroves. And then right now we're testing the sparse configuration where we've removed half of our mangroves in a random pattern. And then our last condition is our baseline condition because we want to be able to characterize the baseline effect of just the flume itself on wave dissipation and see what additional effect the mangroves can provide. Our specimens are built similarly to those we built for our 1/16 scale tests. We're using a mangrove, full-scale mangrove that is modeled after mangrove measurements that were taken in the Florida Keys in Rookery Bay, Florida. Here you can see sort of the idealized specimen drawn in SolidWorks, and here you can see an image of what one looks like during construction in the laboratory. We're using common construction materials, PVC and cross-linked polyethylene or PEX, with similar trunk diameters and prop root diameters to the mangroves that you would expect in the field. Model construction, one of the things as a PI that I wish I could be out for in the age of COVID was to help out with the model construction. It was definitely a ton of work, so I'd like to acknowledge Kieran especially, but also his whole team who were working to make the PEX rigid, string it through, and then install the mangroves. Here you can see just a couple images, but I'd like to call out, almost 4,000 feet of this PEX material that needed to be cut and installed within these mangrove trees. A couple more images of how we installed the mangroves. You can see we used sand to sort of stabilize the bases and then kind of tree by tree strung the roots. And then you can see the finished product and the mangroves filled with our highest water depth tested. Another advantage of the lab is that by constructing these trees directly in the lab, it allows us to characterize the tree from the baseline of the roots up until the top of the highest prop root. This is really challenging to do in the field because you're always working, around high and low tide, and you're never really able to get a fully drained flume like you can here. And so what we're able to do is get a clear variation of the projected area as you move up and down the vertical water column, and allow you to determine how that's going to affect the blockage that's provided based on the projected area of the trunk and root system. Ultimately, we're going to be comparing these LiDAR measurements that we're taking in the lab with LiDAR scans of mangrove trees that we obtained in the field. These are images from March 2020 in St. Lucie Inlet State Park in South Florida. And so we're hoping that we can get very similar blockage areas that we're testing in the lab, and then also that we're verifying with field measurements. Here you can see a layout of the instrumentation that we have in the flume. We have a lot of wave gauges that we're using to measure the reflected wave by the mangroves, the incident and reflected wave in the mangroves, wave transformation through the mangroves, as well as the transmitted wave, as well as the reflected wave when we have our test wall installed. We also have ADVs used to characterize water velocity. We have in the middle of the mangroves a vertical stack of ADVs. You can see a photograph of that here to measure how the water velocities are changing with depth at this midway point through the mangroves. Also using wire resistance wave gauges, pressure gauges, which are actually, I'm very excited about this because we're using these pressure gauges in the field as well. So it will give us a really good validation of these pressure gauges for use in the field. And here you can see the water levels that we're testing in the wave lab. So we have 4 water depths that we're considering, which based on the projected area of the roots, we're considering sort of this maximum projected area, as well as a transition point, and then 2 extreme cases where you would expect most of the root system to be flooded. We're testing irregular and regular wave conditions. We have 3 random wave cases, that's what you see here, and 6 regular wave cases, as well as some tsunami-like long period waves. We're plotting these on a plot of the wave height to water depth ratio to the wave, to the water depth to wave length ratio, which gives us an indication sort of the wave steepness and the wave nonlinearity. The points that we're testing here are shown sort of at the corners of this green shaded area. And you can also see as red triangles, the points that we tested in our 1:16 scale tests, and as yellow circles, the tests that are going on concurrently with the US Army Corps of Engineers 1:2 scale tests. There's a lot of overlap here. All of these clouds indicate individual waves. And we're also excited to compare these tests to see how these identical wave conditions scale between 1:1, 1:2, and 1:16. You can also see in these clouds, we're expecting a wide range of wave conditions ranging from various nonlinearities and also non-breaking as well as broken conditions. And here I just wanted to show a photograph of the tests we have in progress, as well as 2 videos that compare tests at water depth. So hopefully this video works. The first one is showing our wave at our highest water depth tested, interacting with just the trunks of the mangroves. And our second video shows at a lower water depth where you see a lot more of this root system that's interacting with the mangroves themselves. These are just from our hydrodynamic tests. We're also considering wave interaction with the structure after it has been transformed by the mangroves. And I think this is a really exciting application because we're hoping to be able to translate this into potential informative design considerations for hybrid systems, mangrove plus seawall, or how waves interact with the built environment using natural and nature-based features. You can see our test wall. It's at the back of this image here. And then at the front of this image here, the waves are coming from the wave maker and then moving through the mangroves and interacting with the test wall. We have an array of pressure gauges lined up along the center line, and I've labeled each of the water depths that we're testing, as well as where we expect the maximum wave crest to occur. I think you'll see in the live demo that we actually do get some very nice splash up. So definitely some exciting interaction between the wave and the structure. And some other things that we're doing with experiments is testing out new technology. So this is a really exciting application using stereo cameras to characterize a 3D sort of like a point cloud of the water surface. And so this is showing a video for regular wave trials. And we're hoping that we can get some quantitative data that allows us to compare how the water surface transformation is occurring at this specific location as you consider different wave trials and different mangrove densities and different water depths. As I mentioned a little bit ago, we're also using our RBR pressure sensors, which we've been using in the field, and hoping to verify that instrumentation by comparing with co-located wire resistance and ultrasonic wave gauges in the lab. Because ultimately what we'd like to do is be able to say, these are all of our lab measurements, and can we validate that with real measurements from the field? So ongoing plans we have are to measure wind wave attenuation through mangroves through a long-term deployment in a remote island that is west of Key West here in Man Key, as well as to consider mangrove interaction with other types of waves such as boat wakes, which often create heavy stressors on shorelines just due to the heavy boat traffic that many of these places see. And here are two images of the US Army Corps of Engineers experiments. These are under construction photos. The experiments are currently underway, and I'm really excited to be able to compare the data that they obtain at 1:2 scale with the 1:1 scale that we're going to be measuring from the large wave flume to see how any scaling effects could occur as you move from full to 1:2 scale. As I mentioned, we have some overlapping water depths and wave conditions, which I think will be a really nice way to actually characterize exactly how scaling effects come into play. And then just as a heads up, our live demo is coming up soon, so please hang in there for just a couple more minutes. The other exciting application I wanted to talk about is a collaboration with the SimCenter using the UQ tool. Dr. AJ Harris from UC Berkeley is working to create a digital twin of the large wave flume. And the vision for this tool is for experimental PIs, such as myself, to be able to directly import our data into Design Safe, into the data depot on Design Safe, and then use the high performance computing workspace on Design Safe to allow for cloud-enabled simulations. Here you can see sort of one of the versions of the HydroUQ tool. This tool is designed to characterize the building response based on shallow water as well as high fidelity numerical models. And it's a really collaborative process. So one thing that the SimCenter has expressed a lot of interest in is getting feedback from PIs. And so if you have things that you're interested in modeling or that you're interested in putting into the HydroUQ tool, I definitely recommend you go to the website, and they have a survey where you can give feedback and provide sort of a wish list of what you'd like to include in the data. So now we're going to jump over to the live demo. I posted the link in the chat just a couple minutes ago. I'm going to stop sharing my screen and jump over. I think, Pedro, thank you for turning on your video. And I think I stopped my share, so I'll escape from mode here and jump over to our view of the large wave flume. Let's share. Lab, and then I'll put this in full scale mode. If you'd like to view this on your own browser, just in case there's any connection lag, feel free to do that. The waves I think are generating, it takes a couple seconds for the video to actually upload the feed. So one thing that I'll share just while we're waiting on the live stream, you can see it on Pedro's camera, so feel free to blow up his camera. But as a PI, it's been so useful for me to be able to check out the live stream. I've definitely been able to feel like I'm involved in experiments, even though I can't travel owing to COVID-19 restrictions. And I think this has been just a great tool to really continue to stay up to date with what's going on with the experiments. So the waves should be coming soon. can see them on the screen. Here we go.
Tori, this is Matt. While we're watching the video without sound, maybe we could answer some questions that the attendees here have had. Is that okay?
Yeah, that sounds
great.
Do
you want to talk a little bit more about the tests going on?
Oh, yeah, I'm so sorry. Thanks so much. Yeah, so the tests that we're doing, I'll just share briefly, and then we can also answer some questions. The test that we're doing right now is at our intermediate water depth. So the water depth at the vegetation is about 1.45 meters. And our wave period is 6.9 seconds, and our wave height is 0.92 meters. So these are definitely some good waves to sort of show lots of breaking going on, lots of high splash up with the wall. And I think the time series is ongoing, but if people have a question, I'm happy to answer that now, or maybe I could go ahead and jump back to the PowerPoint just to sort of wrap up and then take questions at the very end. Feel free though to kind of keep the live screen on your own browsers, and then we can just wrap up here. Because I just have really 1 or 2 slides. All right, and so just in conclusion, let me get the presentation mode. I sent a photo to my family of this image while we were doing some field work last March. We can't put our feet up just yet, though. I have to say there's a lot of work to be done to understand how these systems perform. A lot of work from the research side to understand how scaling effects impact laboratory studies, but also can we model these systems and can we quantify the uncertainty and inherent variability within these systems based on mangrove growth patterns and natural mangrove densities. Also collaborating with professional engineers and engineering firms who are actually doing some design of these systems for coastal protection, I think is really important to continue those conversations. And then finally, just continuing to advance the technology within our own experimental facilities through developments of stereo imaging, through our collaboration with the SimCenter and the Large Wave Flume digital twin. So with that, just you can see sort of the funding sources. Many people helped us with these tests in this project, and happy to take any questions at this time.
Great. Professor Tomacek, thank you for the presentation. And to Pedro and Dan at Oregon State, thank you for pulling off that live stream. That was really great to see both the what led up to the work and then seeing something happening live is fantastic. So we have a few questions. The mangroves in your model are all planted in a grid pattern. Do you think planting them in a more natural, random pattern would affect the results?
That's an excellent question. And so we're actually really excited about the second configuration we have of the tests we're doing right now, where we have that more random configuration of mangroves to see how that affects wave transformation. There are some studies out there, some numerical studies that have tested wave propagation through cylinders spaced in a grid array, as well as randomized placement of the cylinders. And those tests have shown that it tends to matter more the projected area, so the actual blockage provided by the vegetation, than the random or regular spacing or orientation of the vegetation itself. So we're anticipating that it does not matter whether they're randomly or regularly spaced, as long as the projected area of the vegetation is the same.
Okay. And then a question about maybe scour or erosion around the mangroves. Do you investigate the effect of the mangroves on seabed erosion, or what happens when these waves are occurring?
That's an excellent question. And sediment is definitely a big area of research, particularly its interaction with mangrove prop roots and how waves, and especially extreme wave conditions interact with the mangroves as well as the sediment. It's known that mangroves trap sediment, and so they can actually lead to accretion, but I think that has two effects. One is that it will change your bathymetry. So compared to a no mangroves case, you're actually not even going over the same bathymetry because you also have this trapped sediment and sediment accumulation there. I will say though, I think a lot more tests need to be done to understand how sediment interacts with mangroves and where it goes during extreme conditions.
Okay. It was really fantastic to see the experiment happening because the wave splashing up was very impressive. And so the question is, are the waves realistic to what houses endure during Irma?
Yeah, that's a great question. And so I think definitely some of the conditions that we are testing are towards that extreme side. So during something like a Hurricane Irma situation, we also have less impressive wave conditions, but maybe more commonly expected. So these lower return period where they might happen a little bit more often, and you could sort of expect on it more of a day-to-day or the 10-year storm type conditions.
Okay, and another thank you for a great presentation. The question is, what has been done to ensure the similarity between the real mangroves and the PVC models in terms of their characteristics and strength and stiffness?
Excellent question. And so we actually did some tests looking at the elasticity of the mangrove prop roots. And that was during our initial tests looking at just characterizing our 1 to 16 scale models. And what we found was that they're trees. And so they're pretty rigid. It's not a perfect, rigidity, but for the purposes of the lab experiment, we're idealizing these systems as rigid. And I think another really important point of future work is how does that idealization actually affect the mangrove trees, that assumption of perfect rigidity.
Okay, more questions about the mangroves. In comparison to a random shock dynamic model, how much added damping could be provided by the mangroves? I'm not sure if that's clear. A follow-up question is, how can the dynamic water pressure profiles be affected by the mangroves?
That's a good question. And I hope that this question or this response answers your question. But basically, as waves are going through the mangroves, what sort of the basic theories say is that the waves do work on the mangrove trunk and prop roots. And so they are losing energy as they go through the mangroves. That being said, that definitely requires a lot of calibration of things like drag coefficients, modified Morrison equations to understand the wave attenuation. And that's something that we're hoping to learn from these tests, is a little bit more understanding of how waves dissipate through these mangroves.
And one last question as we are wrapping up in our hour. Is there a similar natural structure like this on the Pacific coast or elsewhere in the world?
That is an excellent question. And I will say that I definitely don't want to overstate my expertise here. I am not an ecologist, although I think that ecologists are excellent people and they need to be involved in engineering conversations, particularly from an engineering with nature perspective. So I would love to follow up with that question, maybe via email or maybe offline or something, but not that I know of, although don't take any stock in my response here.
Okay, one last question because it came in all the way from Europe. So thank you for joining us at this late hour there. The question, the comment is that I thought I saw some waves on the wave steepness dimensionless depth plot. So this is going back to your graphic, that were outside the breaking limit line. Could you comment on that?
Yeah, so
showing
that's a great
measurement
question.
errors?
We definitely had some waves that were anticipated to be breaking by the time they reached the mangrove. So those types of waves, we expected them to be breaking before they reached the mangrove forest. And something that we're very interested to see is how mangroves can enhance breaking wave dissipation, or how potentially they could dissipate wave energy to prevent waves from breaking, or to change, potentially change the wave breaking characteristics owing to the energy dissipation through the mangroves themselves.
Okay. You know, I thought it was the last question, but you're we have lots more coming in. So if you can bear with us. One question is about the scaling issues or scaling that you've done in your models. And I guess somebody's asking about, have you looked into the scaling in these models?
So definitely we're really interested in how scaling can potentially impact the measurements that we're obtaining in the laboratory. And so I think at a 1-to-1 scale, we can pretty confidently say that we're not going to be affected by scale issues. And I think as we move from a 1-to-1 to a 1-to-2 scale, I'm very, very interested to see how wave attenuation either changes or not. Maybe 1-to-2 scale, you know, hopefully we don't see large scale impacts there. And same as we move from 1-to-1 to 1-to-2 to 1-to-16 reduced scale. Hopefully we can confidently say that at these, you know, reduced scales, we can perform more tests, because I'll tell you, it's a lot cheaper and easier to build a 1-to-16 scale model than it is a 1-to-1 scale model. But I think this will give us a lot of clarity on what types of things we need to be doing through physical modeling so that we can understand the way these systems perform in the real world.
Okay, well, I think that wraps up our last question, but thank you so much for taking the questions. To the attendees, thank you for your attendance today, for the questions for Professor Tomacek. And I would like to say that I thought that the live stream from Oregon State was fantastic. So to Dan Cox and Pedro Lamonaco at Oregon State, thank you for pulling that off. Professor Tomacek, thank you for this presentation and introduction to nature-based resilient coastal engineering solutions. We look forward to seeing the literature on that's produced by those tests conducted today. And so thank you very much for the presentation, and thank you to the attendees for joining us. And this concludes the webinar.
Thanks so much.